Now in this lecture we shall be discussing about the properties of universal beams. Now these are the steel beams that are most widely used when we are talking about the Australia. And as an engineer we should first understand what exactly is the meaning of the name and what exactly are the properties and how the properties can help us in evaluating and applying the structural steel members for different applications. Now first of all, when we're talking about the universal beams, the name itself, here you can see that it denotes the approximate depth that we are dealing with. So let us say if we are talking about this particular UB, that is the maximum size that is available in Australia, and that is 610. So it means that approximately the depth of the section that we are dealing with is approximately 610. So in here you can see the meaning also. So if the designation is 610 UB 125, it means the depth of section is approximately 612 mm. After that, the flange. And before that, if we are denoting the depth of the section, it means that from extreme top to the extreme bottom. So that is the meaning of D. After that, when we are dealing with the flange, so if we're talking about the I section, this is known as the web and this is known as the flange. So in here, if you're talking about the flange width is approximately 229 mm. And the thickness of this particular flange, that is approximately 19.6 mm. After that, if you're talking about the web thickness, so this is basically the web. So for web, the thickness is approximately 11.9 mm. And after that, root radius. So root radius is basically when we're talking about the hot rolled sections, there is this slight curve that is given here. So that curve we can see say that that is a requirement of the rolling itself, that there should not be a very strict 90-degree angle. There should be some rooting here. So that is known as the root radius. So if you'll zoom in here you can see that this is basically the R1, that is root radius. So that is approximately 14 mm. So if you're talking about the different requirements, so if you're talking about the bending, or we can say bending members, the main aspect that governs the design are the flange itself, because flange do provides the, we can say, strength against the bending. But if we're talking about the shear strength, so if we're talking about the shear strength, we do need to understand that this is the web that is basically playing the role. So if we increase the thickness of the web, our shear strength increases. If we decrease the thickness of the web, our shear strength decreases. So with the 610, we can say depth alternatives, this is the section that is having the maximum shear capacity, and this is the section that is having, in comparison to these two, the lesser shear capacity. After the depth between the flanges, that is just a number that has been calculated by, we can say, 612 minus the flange thickness into 2. So that gives us number approximately 572. After that, there are these two terms that have been given, that is D, we can say D1 by TW and B1 BF minus TW divided by 2TF. So this is basically the term that help us in calculating the classification of the section. The classification of the section as per Australian code is compact and non-compact and slender. So how we can calculate the, we can say these two procedures, that is basically a different calculation. But in that particular calculation, these are the parameters that help us in calculating the element slenderness. So as per the Australian code, we do need to calculate the web slenderness and flange slenderness differently. So if we will refer to this particular figure here, so this is the figure that has been taken and provided by Computers and Structures in their help manual for ETABS. And this is basically taken from AS 4100 2020. That is the latest code for Australian design. And in here, basically, there's this difference that when we are dealing with the, we can say, flange, we are dealing with this particular we can say equation, that is bf minus tw divided by 2df into square root of fy by 250. So if we are dealing with fy as 300, we do need to multiply whatever number that we are having here by this particular value, that is 300 by 250, and bf minus tw by 2df. So one steel has helped us in, or we can say uh, they've separately given us value so that we can save our time and calculate this particular value in a very quick calculation. So d by tw, that is basically h by tw in this particular language. So h by tw and into square root of f by 250, that is basically helping us in calculating the web slenderness, we can say, value. So we shall be studying in detail about these particular two values. And after that, gross area of the cross section. So gross area of the cross section is the value that help us in calculating, or we can say that basically plays a major role when we are talking about the compression capacity uh, of the particular I section. So uh, I section and universal beam both means the same, because we are basically dealing with I shape section. So when we are dealing with the gross area, so gross area can be simply multiplied with the, we can say, the yield strength, and that is again multiplied with a separate number x, and that x is basically dependent on the, we can say, length of the member that we are taking. So that we shall be discussing in detail in the compression member lectures. But as of now, when we're talking about the flange, the parameters that we shall be discussing or governing are the bending members, or we can say bending capacity. If you're talking about the web thickness, the parameter that is governing is basically the shear capacity. And if you're talking about the gross area of the cross section, the parameter that we are basically dealing with is the compression capacity. So compression, shear, and bending. After that, these are the properties that are basically very important. And before that, we do need to understand about why we are dealing with two different kind of properties here. That is, one is about the x, one is about the y-axis. So before that, I just want to draw some figures here. So let us say we have to, we can say, make a bridge from this point to this point. So we have like one support here, and we have like second support here, and we want to make a bridge from left point to the right point. So for that, we have to make or install an eye girder here, or we can say universal beam here. So whether we do need to install this particular beam like this, or we can install the beam like this, obviously the answer should be this particular arrangement. This particular arrangement, the universal beam is having much more strength as compared to this particular arrangement. The reason is basically the distribution of the structural steel from the axis that we are dealing with. So in broad terms, we can say that the arrangement or configuration of the structural steel is basically talking about a two axis. One is this particular axis, and the second is this particular axis. So we do need to understand that one axis is basically the major axis, second axis is basically the minor axis. So that is the principle of the two different types of values that we are dealing with here. So if we are talking about the x-axis here, this is basically the x-axis, and this is basically the y-axis. Now, if we compare the properties, we can see that these values, that is about the x-axis, are much higher as compared to the y-axis. And in parallel, we can understand these two figures that if we are aligning the member with some with arrangement something like this, that is our structural steel member is basically like something like this. That is much more stronger as compared to the structural steel section having like this. So we can say that, let me just draw the isometric here. So we can say that our structural steel itself, that is, we can say much more stronger when the axis is something like this. But our structural steel section is much weaker when when our axis is something like this. So in your mind, we have to understand that axis orientation is a little bit confusing when you have just started understanding the structural steel engineering. That if we are drawing the axis like this, it means that throughout the length of the member, your axis is something like this. It means that from this particular point, your structural steel is either up or either down. That is, your structural steel is distributed for this particular orientation. So we can name it as X, and that is the stronger axis. So in terminology of the structural engineer, this is basically the major axis. Or just to have a clear, we can say, uh, representation, this is basically the stronger axis. And if we are talking about the YY, this is basically the YY axis. So this is basically the minor axis, or we can say weaker axis. So we can now open that particular property table again. So here we can see for x-axis our values are, as we have discussed, that higher. For in against x we are getting 986 as the value, but when you're talking about the y, that is minor axis, we are having only and only 40 as the value. So that is how much difference it can create when we are dealing with the orientation of the structural steel members. So after that, if we are talking about the meaning of these Ix, Zx, Sx and Rx. Now you might have discussed these values in your college lectures, but it is very important to understand that these values form the basis for understanding the structural steel calculations or structural steel engineering. So we can just open these values here. So if you're talking about the I, or we can say Ix, Iy, that is basically the second moment of area. If we are dealing about the, we can say, Zx and Zy, we are talking about the elastic section modulus. And if we are talking about the Sx and Sy, we are talking about the plastic section modulus. So we can, what exactly is the difference between the elastic section modulus and plastic section modulus? And what is the meaning of the second moment of area? Now, second moment of area, we all have, studied in detail in the, in our university engineering, that how we can calculate the second moment of area about I section if we are talking about this particular axis. That is, we have to have two different theorems, and on the basis of that we can calculate the second moment of area. The formulas are different if we are dealing with box sections, and formulas are different if we are dealing with the, we can say, solid rectangular profile. So for example, for solid rectangular profile, it is simply BD cube by 12. So this is basically the B and this is basically the D. So that is the calculation for, we can say, moment of inertia about this particular, sorry, the second moment of area about this particular axis. And after that, why we are dealing with two different types of sectional modulus and what is the meaning of the elastic and plastic. Now that is basically the theory. That is again very confusing if we have just started the structural steel engineering. Now before that, we do have to understand that the basic graph of the stress strain, we can say, for the structural steel as a material. So we all have studied in detail about this particular graph that we are discussing here in our universities and higher education. So we can say that like 20 to 30 years back, we all were thinking that structural steel should remain fully elastic only at the time of the loading or at the time of the extreme events, we can say. So broadly, majority wise, we can say that we were only dealing with this particular area. And across this, we were saying that the structural steel shall remain fully, and we can say should remain fully elastic at the time of the earthquake. But as the research progresses and as there is development in the structural steel engineering also, we have calculated, or we can say we have assessed that if the structural steel profile itself that is very strong, and we can say the distribution or the thickness or the arrangement that is very sturdy, we can go a little bit higher also. That is, we can go up to plastic, or we can say we can allow plastic deformation also. And in that plastic deformation, it is not that structure shall not collapse, but what will happen is that there shall be plastic hinge formations. And plastic hinge formation is basically we can say a concept that is much more prevalent in high seismic areas. So what will happen is that, let us say this is basically the warehouse structural steel frame that we might be constructing. So it may happen that there may be a hinge formation here, there may be a hinge formation here, and there may be hinge formation here at the time of the earthquake also. So that is basically the basis that let us say this is the profile, and this particular area shall receive a lot of twist and restraint, or we can say twisting at the time of the earthquake, such that material goes up to fully plastic, but at the same time it does not collapse. So that forms the basis that why we are dealing with the elastic section modulus and plastic section modulus. So it is not that we do need to consider the plastic properties for all kind of structural steel members. First of all, as I said, the section itself should be compact. If the section is we can say slender, or if the section is non-compact, then we should not be dealing with the plastic section modulus, or we can say plastic properties of the structural steel members. So after that, we have discussed Ix, Zx, Sx and Rx. Now Rx is again something that is basically the radius of gyration. So we have discussed about Ix, Iy, Zx, Zy, Sx, Sy and Rx, Ry. So Rx, Ry is basically the radius of gyration. So I hope the concept is now clear to you that the properties of different kinds of structural steel members that should be like understood before we proceed further. So we can come back to this particular table again. Ix we have understood. Ix is the second moment of area. Zx is basically the elastic section modulus. Sx, as we can understand here, that is again a little bit higher as compared to the elastic section modulus. And there is one more term called form factor. So we can say plastic section modulus is equal to elastic section modulus into the form factor. And this form factor can be calculated by again different calculations, and it can be easily calculated from this particular values also. That is it is nothing but 3680 divided by 3230. So similarly, about the y-axis, we can again see that second moment of area, Zx, Sx and are y. Now just to, if it is a little bit getting confusing again, why the properties are a little bit lesser in the other axis. Here we can understand that as we know, our structural steel goes away from the neutral axis. It adds more strength to your section. That is, our second moment of area is higher. Our we can say elastic section, or we can say plastic sectional modulus, both of them are higher. So if we're talking about the other axis, that is y-axis, the structural steel itself is sitting on your neutral axis itself, or on your axis itself. So we only have these profiles getting away from the neutral axis. So that is why this value, that is Iy, Zy and Sy, they are very low for the perpendicular axis or for the minor axis. So in this lecture, we shall be discussing about using the terminology that this is basically the major axis and this is basically the minor axis, because this becomes very important when we are planning the structural steel configuration of the building.